Okay, my friends, so a little bit of history here. And this history starts with the, well, I guess it's now world famous Guinness Brewery. Well over 100 years ago, Guinness wasn't the household name it's kind of become. For all intents and purposes, it was a microbrew, kind of like the 5 or 6 that sprout up every couple weeks here in Bend. But Guinness always wanted to be bigger than a little tiny Irish beer. So, in a very novel move in the late 19th century, they decided to use statistics to take their beer to the next level.
You put an ad in the paper.
They did indeed put an ad in the paper. It was a short ad, got right to the point, and it was designed to shake loose the best number crunchers in Dublin.
Rednecks and Southsiders need not apply.
And find a data analyst they did. Meet William Gossett, hired in 1899. His job was simple. He's a statistician, but he's also a taste tester. He needs to figure out what the nuances are between the different strains of Guinness. The obvious problem, of course, is how do you do this without getting completely lit? So, Gossett figured out that he was not going to be able to drink inordinate amounts of beer. He has to draw small samples. But the bell curve only works well on slightly larger samples. So his job, or his solution I should say, was to create a new distribution that had the same properties as the bell curve, but worked on smaller samples. Okay, so what did Gossett come up with? He came up with something totally awesome. He called it the student's tea distribution. We're going to call it the tea distribution. We dropped the student's part off, generally speaking. I'm not even sure why he called it that. He couldn't name it after himself because Guinness had a weird rule about employees publishing things under their own name. Not sure why he called it student's tea, but whatever, we're stuck with that now. But here's the badass part. The only constraint of the tea distribution is the sample size. That means the curve itself depends on the sample size. Now, this is the part that boggles my mind, blows my absolute mind. Okay, the formula for this thing and how he got it. He did basically a Monte Carlo simulation, but this is 1899, right? Nobody was using computers in 1899. They didn't exist yet. So he had to generate a Monte Carlo simulation by pulling pieces of paper out of a hat. Oh my God, the coolness of this is off the chart. Now, this is not a math class, so I'm not expecting you to get as excited about that equation as I do. But if you compare that to the bell curve, you can see how the one that Gossett came up with is phenomenal for actual experimental statistics. The only variable in there is n, not this weird assumption of a mu and a sigma that we have to know ahead of time before we can use it. It's ridiculous. We don't. Now, not a math class, so let's not talk math. Let's take a look at how his curve looks when compared to the bell curve. Okay, my friends, so what you're looking at here is you're looking at the Z curve, which is in blue here. That's the normal curve. That would be the curve that we pull the confidences off of for proportions. And then you've got your T curve, which is this red one here. Now, the first thing you probably notice is that the red curve itself is lower in the middle and fatter in the tails than the blue curve. They both contain 100% area. The area under them is the same, 100%. Everything has to be under there. But the T curve has less in the middle and more on the ends. Okay, so I know I'm a huge geek, but this is probably my favorite part of Gossett's T distribution. The fact that the average of his distribution is lower than the average of the bell curve and the tails are fatter is going to make us take more caution when forming confidence intervals on small samples. It's going to necessitate the fact that we're going to have to go out wider. Remember, as sample sizes go up, margins of error shrink. But we don't talk much about what happens when sample sizes go down. Well, the inverse is going to happen. So with small samples, Gossett's awesome formula with its ends in the right place are going to force our intervals to be wider. And as sample sizes increase, it's going to force them to come in, just like they did before. Such a cool curve. Okay, now let's start increasing the sample sizes and see what effect that has on the T curve. So let's go to sample size of 3, 4, 5, and hopefully you're noticing, as we do this, the T curve is beginning to do a couple things. First of all, the center is beginning to approach the bell curve, and the tails are as well. So the center is rising and the tails are falling. And if we keep going, you're going to notice that eventually there's going to be a point when they effectively are the same curve. Now, if we zoom in really far, there are going to be differences from one curve to the next. But at this point, they're effectively the same curve. Okay, a teeny tiny little bit more history, and then we're going to get into actually running the calculations on these things. A couple things that bug me over the years about the way this subject is classically taught. First off, for years, and I think some people are still doing this, they've taught confidence intervals for means in 2 days, if you will. They've done it the first day. If your sample is small, then you should use the t distribution. But if your sample is large, you could use the t or the z distribution. And that bugs me for 2 reasons. First of all, what does large mean? Like you just saw that once we got above, like, I don't know, a sample size 20, the t-curve basically nudges up right into the bell curve. So I'm not real sure how large a sample has to be until it's close enough. That's number one. And number two, let's just think about this for a second. If you have a small sample, let's suppose we could agree on what small means. If you have a small sample, you can use t. If you have a large sample, you can use t or z. Why not just always use t in that case? It doesn't make any sense, right? I mean, take a look. Here are t critical values, t confidence multipliers for 95% confidence for a different number of sample sizes. And you can see right away that as the sample size gets larger, that multiplier gets closer and closer to that 1.96 that we know the bell curve has. So the t is going to be fine at large samples or small samples. Let's just use it for all the samples. Okay, I feel better getting that off my chest. I am not going to anticatedly make you go to old school charts and tables to get those confidence multipliers. No way, no way. I've got a spreadsheet that pulls them for you. All you've got to be able to do is if I give you data from a sample to be able to pull off the sample average, the sample standard deviation, and obviously the sample size. Once you have those 3 things, I'm going to have Excel calculate the rest for you. Let's do that now.